Hello and welcome to my first online program, free program for very serious, hardworking, and aspirants. So while I say serious, I don't mean to become serious. I always harp on learning, teaching with all fun, pleasure, enjoying your every moment while learning, while disseminating your experience as a teacher. Everything should be done with a lot of fun, pleasure, and enjoyment. No duress at all. Now, today we are going to start a chapter which is very interesting. And as I have already told you, and I am telling time and again, that our program will be concept based. Now, in atomic structure, before we enter into the intricacies of orbitals and their participation in bonding, we must know how the electrons are situated around the nucleus. Now, for that, we must recapitulate what we learn about a wave, electromagnetic wave, radiations, any transverse wave or any longitudinal wave. We are dealing with electromagnetic radiations, which are transverse waves, and every wave has a wavelength from crest to crest or from trough to trough, that is called wavelength lambda. And its usual unit here is angstrom or nanometer. And as you know, 1 angstrom is equal to 10 to the power minus 10 centimeter, or 10 to the power minus 8 centimeter, or 10 to the power minus 10 meter. And 1 nanometer is 10 to the power minus 9 meter, or 10 to the power minus 7 centimeter. So that means it is a unit of distance. And another is called nu, that is called frequency of a wave. Can you tell me, Aaron, what is frequency?
Uh, Sir, number of vibrations per second.
Yeah, you are correct. But I can put it in a different way, that number of full waves passing through a particular point. So supposing we start from here to here, it is a full wave, or from here up to here is a full wave. From crest to crest or from top to top is a full wave. How many waves are passing through, number of waves passing through a particular point per second? So its frequency here is 1 by second, or sometimes second inverse. Some people call it hertz. In chemistry, mostly we will be using per second, because number of waves has no unit, so only 1 by second or per second is the unit. And there is another interesting, uh, Arman, good morning. Arman.
Yes, sir. Sir,
Hmm.
namaskar.
Namaskar. So we have already started atomic structure. I am just introducing, in rather I'm recapitulating your memory, that a transverse wave, like electromagnetic radiations, every wave has three properties to express it. One of them will be sufficient, like lambda, wavelength, from crest to crest, from trough to trough. It is a distance unit, but here we mostly express in angstrom, which is 10 to the power minus 8 centimeter, or 10 to the minus 10 meter, or in nanometer, 10 to the minus 9 meter or 10 to the minus 7 centimeter. And there is another property of a wave called frequency. It is the number of full waves. Start from here, here, and here. This is a full wave from crest to crest or from trough to trough. So the number of full waves passing, supposing we start here, this is a full wave, a crest and a trough. Start from 0 and then go to the maximum amplitude, come back to 0, go to the maximum negative amplitude, and then come to 0. This is a full wave, a cycle. And the number of such waves passing through a particular point per second, 1 second, that is called the frequency of a wave. So unit is second inverse. We can call it in physics, they call it hertz. But in chemistry, we don't write hertz, we write second inverse. And the other important property is wave number. That's very, very intriguing. Wave number is nothing. The symbol is very misleading. I don't know how and why. Scientists borrowed the same symbol for wave number. Should they not get another symbol? Nu bar. That is nothing but 1 by lambda. Reciprocal of wavelength is called lambda. Nu bar or wave number. So the unit is centimeter inverse or meter inverse, not angstrom inverse. There is nothing called angstrom inverse. Angstrom is an ornamental unit, not a unit for calculation. Centimeter inverse or meter inverse. So, interestingly, you can feel that electromagnetic radiations, you can have a look. I will share all the files and I will check how much attentive you are. You will be writing at your home. These are the 1, 2, 3, 4, 5, 6, 7, 8 electromagnetic radiations in increasing order of their wavelengths. This wavelength is in angstrom. So the lowest wavelength electromagnetic waves is called cosmic waves. They are released from sun. So 0.001 to 0.01 angstrom. Angstrom is 10 to the minus 10 meter, 10 to the minus 8 centimeter. Then followed by gamma rays, which are produced by radioactive elements. That their wavelength range is 0.01 to 0.1 angstrom. Then followed by X-rays, which are produced mostly artificially by bombarding electron beam with a particular energy to an element, which is hitting the core elements and then knocking it out. When the higher electrons, they come back to the lower state, they emit another type of radiation that is called X-ray, and its wavelength is 0.1 to 150 angstrom. Followed by ultraviolet rays, which also comes from the sun, and they are being arrested by the ozone layer, stratosphere, but we are making holes because of our mischief. And so that is why we are also being affected by some, leaking ultraviolet rays from the ozone layer. Then visible, which we can see, or through which we can see, is ultraviolet is 150 to 3800, and visible is 3800 to 7600. Usually we say 4000 to 8000. For better memory, we say 4000 to 8000 angstrom, but actually 3800 to 7600. This is the violet region, VIBGYOR, and this is the red region. And this change is gradual. And then infrared rays, 7600 to 6 times 10 to the power positive 6. So great range, 7600 angstrom to 6 times 10 to the power 6. Microwave is from 6 to 10 to the power 6 to 6 into 10 to the power 9. Then finally comes the longest wavelength radiation in nature is radio waves, through which we watch TV, we listen in radios. So these are long wavelength radiations, 6 into 10 to the 9 to 3 times 10 to the 13. You must write in your copy this table. I think can you quickly write down this range because we'll be solving problems. In my class, guys who are watching, who will be watching later in YouTube, which I will upload after the class is over, you must be with the lecture, my lecture, with a copy, a dedicated copy. And whatever I ask you to write in the lecture program, you write, not much. But after, when you prepare your notes, then you can write. I shall be giving the details which you can write, because all things a bright student like you are is not supposed to write and while away the valuable time in the lecture program. So you just write down this while I am talking. Hello, Prabhu. Good morning. These are the electromagnetic waves in the increasing order of their wavelengths. Cosmic rays, 0.001 to 0.01. You write down quickly. Gamma rays, 0.01 to 0.1. X-rays, through which we take the photos of our broken bones. X-ray. Ultraviolet rays, which come from the sun and being arrested by the ozone layer. But still nowadays, many ultraviolet rays are coming down to the earth and creating a lot of health problems, not only to human beings, but also to the agriculture. Then our most favorite visible rays through which we are able to view, to see an object. Then infrared, these are called the heat radiations, from 7,600 to 6 into 10 to the 6. And then microwave, through which the telecommunication, all the telecommunications, the satellite communications, they go via microwaves, and then radio waves. Have you copied?
Yes, sir.
Okay. Now, the interesting thing here is, for all electromagnetic radiation, the lambda is inversely proportional to nu. Less is the lambda, more is nu, because at a particular point, more number of such squeezed waves will be passing per second, and longer is the wave, less number of such waves will be passing per second. So nu and lambda, they are inverse related, and the proportionality constant is nothing but c. As we fondly say velocity of light, but actually it is velocity of all electromagnetic radiations. Not only light, but also UV, X-ray, gamma ray, radio waves, microwaves, IR, all radiations in space, that is in air or in vacuum. If you change the medium, undoubtedly the C value will change. But we say C, the velocity of light, fondly, commonly called velocity of light, but actually it is not the velocity of light alone. And its value, approximately 3 times 10 to the power 8 meter per second, or 3 times 10 to the power 10 centimeter per second. And since we already know another parameter, that is nu bar is equal to 1 by lambda. Oh, I'm sorry. Here I have done a mistake. Lambda is equal to C by L. So this we already know. Nu bar is called wave number. So we can write down here, you take nu here and bring lambda down, so that this can be C nu bar. So nu is equal to C into nu bar. Because 1 by lambda, you bring lambda to the right side, take nu to the left side, and then it becomes 1 by lambda. In place of 1 by lambda, we write nu bar. This is the wave number. This is the constant, which is same for all electromagnetic waves, and this is its frequency. So you can correlate between anything to anything. Supposing I'll ask you a question, how quickly you carry a calculator with me. Whenever you are watching in the video, you always carry, you can take permission from your parents to use the calculator while you are with me, not when you are away from me or your teacher. You can do manual calculation. So supposing I will give you a say I will give you a 3000 angstrom radiation. I want you to find out its nu and nu bar. Quickly find out. This 3000 angstrom means I have given the data lambda. So these are the three. They are interrelated by the constant C. So the moment I will ask you to find frequency, so you relate nu is equal to C by lambda. Lambda is equal to C by nu is equal to C by lambda. So you can C is equal to 3 into 10 to the power 10. Supposing we will use, because you can use meter, because I am using centimeter per second, and lambda is 3000, and in angstrom for calculation immediately change it to 10 to the minus 8 centimeter. Centimeter will cancel, and it will remain only per second. So if you borrow 3 zeros into 10 to the power 7, then 3000 will cancel. This is second inverse, only per second remains, and that the answer becomes 10 to the power 7 second inverse, or Hertz. You can write down, no harm. And if I ask you to find a nu bar, either you can use this law, this formula, nu bar is equal to nu by C. If nu is equal to C nu bar, so nu bar is equal to nu by C. But I usually do in the other way, 1 by lambda. Nu bar is equal to reciprocal of wavelength. So 1 by 3000 angstrom is 10 to the minus 8 centimeter. So let us take 10 to the power factor is to the numerator, it becomes plus 8. This becomes centimeter inverse. So borrow 10,000 into 10 to the power 4, so that we can have a value, scientific way of expressing your answer. So this becomes 3 zeros get cancelled. So it is 3.33 recurring 10 to the power 4 centimeter inverse. So the wave number of the wave I gave you is this one, and the frequency of the same wave is this one. Did you do it in your copy?
Yes, sir.
Now, can you remind me, this 3000 angstrom belongs to which category of electromagnetic waves? Do you remember? Oh, you have already copied. You look to your
Sir,
copy.
visible rays.
Arman, who said visible?
Sir,
Sir,
visible.
Arohan, sir.
Arohan. Which belongs to visible? Good morning, Prabhu. 3000 belongs to visible.
Sir, UV rays, sir, UV rays.
Therefore, I told you to copy. Prabhu, this is very important. I asked nothing to copy, because you'll be solving a lot of problems. You maintain your notes at home. This is the thing which I told you to write down in my presence, because these are the 7 electromagnetic radiations categories. The wave I gave you, 3000 angstrom, belongs to this ultraviolet rays. It doesn't have any color. Excepting visible radiations, no other radiations will help in developing any color. They are colorless. Only these are colored from 3800 to 7600. So once I give you, supposing I'll ask you the other way. Supposing I give you a radiation having wave number nu bar, say 2000 centimeter inverse. You will find its wavelength in angstrom and also find its frequency in hertz. This angstrom can be nanometer. There can be so many alternatives. Usually angstrom and nanometer you express in both. And new frequency only has one unit, that is hertz, or in chemistry we use second inverse. Same. Cycles or waves per second is hertz. So funnily I say chemistry people, they do not use cycles, bicycles. They use EVs, electric vehicles. So we eat away cycles and we keep only second, that is in the denominator. So often we write second inverse for frequency. So can you calculate for me, the quicker the better? We are recording this program. This will be benefiting anyone who will be watching later, and those who are watching later, make it a point to pause the video whenever you are going, thinking that it is going rapidly, you missed out something, you pause it and then write down. You can return back and then start again from where you did not understand. I'm sure. And I told you this, Arman and Prabhu, they know that our discussion will be very, very intense, catering to not only the needs of NEET, but also IIT Advanced. Most importantly, concept. You are studying a particular subject. How far you can go in developing the concept? In atomic structure, the most important part is quantum theory and then quantum mechanics. The introduction, the idea of quantum mechanics, the Schrodinger's equation and its application, that will be given to you conceptually. Now, if it is nu bar, then you can find lambda. Lambda is equal to 1 by nu bar, because nu bar and lambda, they are reciprocals of each other. So it is 1 by 2000 centimeter inverse. Supposing I make it angstrom, because I have asked you to angstrom. So this is 1 by 2000 centimeter. What I do, 1 centimeter, who can tell me 1 centimeter is how many angstrom? Yes. Yes, please. Arohan, 1 centimeter.
10 to the power 8.
Yes, precisely. 1 angstrom is equal to 10 to the minus 8. So conversely, 1 centimeter is equal to 10 to the power plus 8 angstrom. So here you convert centimeter into angstrom so that you can simplify the calculation. So this is, that means 10,000 if you bring, keeping 10 to the power 4 away, then 10,000 by 2000 is become 5. This, so what is the result? 5 times 10 to the power 4 hertz. Oh, we are finding, I'm sorry, angstrom, because we have already converted to angstrom. Now can you tell me to which part of the electromagnetic spectrum, which branch of the electromagnetic spectrum does this particular wave? This particular wave, remember, having a particular frequency, particular wavelength, particular wave number, it is called a monochromatic wave. Remember this. or radiation consisting of a single frequency. Single frequency means single wavelength, single wave number. But usually we have a bunch. It's called polychromatic, one lambda. But contrary to that, if there is a multiple hundreds and thousands together, bundled together, it's called polychromatic. Polychromatic waves mixed, more than one. And in the questions that you will be getting, you will be given the data for one wave. So I have given for one wave, it is 2000 centimeter inverse. That is the wave number I am giving. So you are supposed to find out lambda, which we got to be 5 times 10 to the power positive 4 angstrom. So look to your data table and tell me to which region of the entire electromagnetic spectrum does this wave belongs. Yes?
Say infrared.
Yes, sir.
Precisely.
Infrared.
Infrared. It will not be visible. It will be a heat radiation. And then immediately you can find a new. Either you can go for nu is equal to C by lambda or C nu bar. Whichever you, I always say, don't use this relationship. Sometimes students, they interchange. Then becomes entirely wrong. So go with the first principle, C by lambda. Once you got lambda, then C is 3 times 10 to the power 10 centimeter per second. I am not using meter per second. You can use. We'll be doing in some other problem in pure SI unit. And lambda, we have already found out to be 5 into 10 to the power 4. And of course, angstrom, we have to multiply 10 to the power minus 8 centimeters, so that centimeter will cancel. And then it's interestingly 30 into 10 to the power 9 into 10 to the power 8 into 10 to the power minus 4 by 5. So 6 times, कितना हुआ?
10 to the power 13.
Hertz. I thought we will not write Hertz here, second inverse. So the same wave, monochromatic wave, has a wavelength that is 5 times 10 to the power 4 angstrom belonging to the IR region. Same wave has the wave number 2000 centimeter inverse, and same wave has the frequency 6 times 10 to the power 13 second inverse. With this, we shall enter into the Planck's quantum theory. This is quantum theory, not quantum mechanics. Einstein was the first person to suggest that these electromagnetic waves may be visible, may be UV, may be IR, may be any wave. There are 7 categories. And each category has infinite number of monochromatic waves merging into one another. It's not a single wave. It's infinite number, infinite plus infinite, 7 into infinite is equal to infinite. So Einstein was the first person who proposed, which ultimately led Planck to give his theory. But the credit will go to Einstein first. From his famous photoelectric effect, he proved that these radiations, as we feel, that they are continuous. They are not continuous. They are discontinuous. They have wave nature, no doubt, but you feel they are having some packets. This is very abstract to really conceive in some practical demonstration. Only thing you have to conceive that light, and in fact all electromagnetic waves or radiations have dual nature. One, wave nature, okay? That doesn't mean that it is to be continuous. Wave nature, that has been proved beyond any doubt. You shall study the wave nature is conformed by interference patterns, diffraction patterns. There are so many experiments to prove that it's not going rectilinear, rather in a wave manner. That has been proved. But he proved that yes, wave, okay, 100% correct, but not continuous. Particle nature. This particle is called a photon or a quantum. Quantum, this might be misleading. Therefore, people started calling it as a photon. Although photon, in a true literary sense, it means light, visible light. But the word photon became so popular that just like your grandpa will say, "Hey, Arun, please bring the English Samaj." English Samaj bring. Samaj is such a popular word which represents now the newspaper. So English Samaj Lao. That means he's asking to give you some other like statesman or Times of India or Indian Express, whatever. But he's saying bring Samaj, English Samaj. So photon has become so popular. So it is used for UV photon, like X-ray photon, gamma ray photon. Photon is one particle. As if you just vaguely, I can say, it's not the proper way to say, but just can have continuous nature is there. Just you think as if there is some discontinuity. The gap is vacant. So, energy is being propagated, produced by any source, that is emitted, propagated in space, as well as it is absorbed by any body in a discontinuous manner. That is the Planck's quantum theory. Number one, EM radiations emitted, propagated in space, and absorbed. All these processes in a discontinuous manner. In forms of discrete means alag alag, discrete energy packets called quanta or photons. Quanta is the plural of quantum, called quanta. Singular is quantum, but more popularly photons. So this I will tell you later on that how Einstein proved that yes, wave nature is 100% true, but continuity is not true. It is discontinuous and it is going very rapidly in the speed of 3 times 10 to the power 8 meter per second, very rapidly. You cannot even reconcile its discontinuity, but it is discontinuous. It is going in the forms of discontinuous energy packets. Each energy packet is called a photon. And the second one he found, which is Planck's, his own theory, that the energy packet, the energy value of each photon is proportional to its frequency, nu, and hence it's equal to its proportionality constant named after him, h nu. This h is called the Planck's constant. His value, you have to remember, 6.626 times 10 to the power minus 27 erg per atom. This is per atom. Now, this is erg energy This is h. This is 1 by say arc second. I'm sorry, arc second. Because you know this is frequency is 1 by second. So h will be arc second. Not per atom, arc second. That's it. Or in SI, it is 6.626 or 627. Some people write 627. Doesn't matter. 10 to the minus 34 is joule into second. By mistake, I was telling per atom. I will tell you per atom in some other case now, after some time. Well, this value you have to remember. Either in CGS is 10 to the negative 27 and in SI 10 to the minus 34. And since you know the relationship between nu lambda and nu bar, you can write h nu or hc by lambda or hc nu bar. 1 by lambda is equal to nu bar, hc nu bar. So these are the three relationships. Whichever data is given to you, nu, then this relationship. Lambda, then this relationship. Nu bar, this relationship. Let's solve a problem. Supposing I want find, let me see how quickly you can find the energy of a photon having wavelength say 200 angstrom. Can you tell me 200 angstrom belongs to which category of EM radiations?
Sir, UV rays.
Yes, 150 to 3800. Yes, UV. But I want to know the energy packet. I mean, the value of the energy that each packet is carries. Find out for me. Later on, we'll be studying how Einstein, Planck himself, Compton, several scientists, and also other persons like Balmer, they proved the discontinuity nature, the discontinuous nature, the photon nature. You know, let me tell you, Arun, that these photons, they are massless particles. They do not carry any rest mass. When I
Yes,
say
sir.
when I say massless, I mean rest mass. I will talk about what is rest mass and mass in motion, relativistic mass later on. I will not want to put you under any sort of heaviness at this moment. But with time, you will be finding that I will be unraveling the mysteries of all these things which we were studying more and more. So photon has a rest mass equal to 0, but it is a form of an energy particle. But it's moving in wave, no doubt. But it is discontinuous wave, which has been proved by the photoelectric effect by Einstein, the black body radiation by himself, Planck himself, and Balmer was the first person who found the hydrogen spectrum becoming discontinuous. And then Compton later joined, he also proved through his famous Compton effect that energy propagation, emission, absorption, they are not continuous. As you think they are not. So what formula you will be using? E is equal to hc by lambda, because I have given lambda. So h is 6.62. Let us this time use SI unit. 10 to the minus 34 joule second into C is 3 into 10 to the 8 meter per second. So second per second get cancelled. And lambda, let us convert it to meter. 200, 1 angstrom is 10 to the minus 10 meter. So meter also cancels. So finally you are left with joule. So quickly tell me what will be the value of one single photon of the radiation whose wavelength is given 200 angstrom.
9.939 into 10 to the power 18.
9.99.
9.939.
939 into 10 to the power
18.
Oh, plus 18. No. Plus 18.
So minus. So minus 18.
Minus or plus?
The minus.
This is 34. By mistake, I have written minus 3, minus 34. Mind you, I give you a permanent direction that whenever I commit any mistake because of the slip of my pen, please point out because it is being recorded and others will benefit. If there is a minor mistake prevailing or persisting in my class notes, I mean, this is called the lecture notes, not the notes which I will provide, the PPT file which I will provide from which you will prepare your notes, that is different. This is the work I do in the class where I make you understand. So minus 34. I was wondering minus 3 लिख दिया था मैंने गलती से मिस्टेक, तो कितना हुआ 9.9
Sir, 93 into 10 to the power minus 14 joules.
14 1 4.
Yes, sir.
So this is the value of the energy of one single photon of this radiation. Similarly, at home, I have given some practice things, not many, some practice. Like I will be giving nu bar. Supposing nu bar I am giving, say 10,000 centimeter inverse or say meter inverse. So 2000 meter inverse this time and find its energy. And also, I will ask you find to which region does it belong. That means you have to convert it to lambda. Unless you convert it to lambda and check with your table, you can't know that it belongs to UV or IR or X-ray or whatever. Which EM radiation?
Sir, ସେଇଟା 10 to the minus 18 ଜୁଲ ହଉଛି ନା?
Minus 18 ହଉଛି?
Yes,
ଏଇଟା
sir.
minus 18 ହଉଛି?
Yes, sir.
ଟିକେ check କରିବ. Prabhu is claiming that this should be, is it 9.9 10 to the minus 18 or 99 point something or 9.9?
Sir, 9.93 into 10 to the power minus 18.
That means it's not minus 14, it is minus 18, right?
Yes, sir.
Okay. So guys who are watching the video, please make sure that the calculation is correct. If by chance I and those who are joining in Zoom, they commit any mistake, but you can rectify. But we'll try our best not to leave any mistake here in calculation or anything. So if I'm giving you 2000 meter inverse and I'm asking you to find E, then you will use the formula E is equal to hc nu bar, the second one. No, third one. E is equal to h nu, E is equal to hc by lambda, or third one is hc nu bar. So 6 into 10 to the power 6 into 10, 6.626 to minus 34. Remember joule second, there is no need to write. When you use the units uniformly, all SI, then there is no need, everything will be cancelled out, joule will be left out. 3 times 10 to the power 8. Nu bar I have given 2000 meter inverse, all in SI. So nothing to write, so they will cancel. So what is the finally you are getting in joule? In fact,
Sir, 3.972 into 10 to the power minus 24 joules. Sir, 3.972.
okay. Please contest if this appears to be wrong for you, some of you can contest and tell so that he can also check. So, okay, but I wanted to know to which reason. You can just check lambda is equal to 1 by nu bar. Unless you find lambda, you have remembered the hierarchy in form of lambda and that to angstrom. So you have to convert to lambda and in form of angstrom. 1 upon wave number. 1 upon wave number is 2000 meter inverse. So that means it is 1000 by 2000 meter. 1 meter is how many angstrom? Who can tell me? Yes, Arun, Prabhu?
10 to
Anyone?
the power.
So 10 to the power 10.
Yes, fantastic. So this angstrom, because 1 angstrom is equal to 10 to the minus 10 meter. So 1 meter is equal to 10 to the plus 10 angstrom. So you take a loan of 10 to the power 4 and keep 10 to the power 6. And then this becomes 5. 5 times 10 to the power positive 6 angstrom. Am I correct? Please make sure that I am not committing any mistake in calculation. If that is so, you check with your table to which region does it belong.
Sir, infrared.
Precisely, infrared is 7,600 angstrom to 6 times 10 to the power 6 angstrom. This is the widest range. So this falls here. So it is a IR wave. So in this way, you can also be given the value of frequency. In that case, you will use E is equal to h nu. So this is all. Let us bid goodbye to Planck's quantum theory. And that has been proved by so many experiments, including hydrogen spectrum. Now we shall enter into atomic spectroscopy. This is a small little concept. You know the concept of a spectrum from the solar spectrum. You know, when sunlight is passed, a white sunlight is passed through a prism, it is dispersed into 7 colors. 7 colors we say for fun, but infinite number of colors. But to our eye, we visualize VIBGYOR. The shortest wavelength is VIBGYOR. This is a continuous, not, and the pattern that you find in the screen is a continuous pattern. There is no gap in between. I am doing in red, but actually this will be violet, then slowly changing into indigo, then blue, then green, then yellow, then orange, then red. So this dispersion is, that happens through the prism, and the modified form of prism is called a grating, a diffraction grating. That has a greater power of dispersion, a grating that disperses into, this is called a spectrum. The spread of different waves, different, out of a bundle of waves, you can spread. Of course, each region has infinite number of waves, but still you can see a continuous pattern from the lowest wavelength to the highest wavelength. You can see a spread which was not there before passing through the prism. Now you find a systematic, continuous spread of the waves from lowest to highest, from bottom to top, or from highest to lowest, from top to bottom. This is called a spectrum. And spectrum is of 2 types. Basically 2 types. One is emission. The other one is absorption. Usually when we say spectrum, we mean emission. When some body, maybe sun, maybe a tube light, or maybe an incandescent lamp, whatever, a torch, whichever light source is radiating light, that is emitting light, and then we are passing that emitted light through a prism and analyzing it. That is called the emission spectrum. You are able to see all the bundle aggregates spread into some pattern. That pattern is called the spectrum. That is emission spectrum. absorption spectrum is very, very, not very popular, at least for the +2 level. But in higher level in spectroscopy, when we teach to higher graduate, under postgraduate and research level students, absorption spectrum is very popular. When you go to spectroscope will give you an absorption spectrum. That means when it is absorbing, you are recording. But here it is emitting, not absorbing, emitting. Whatever absorption it has already made, it has already made. But when it is emitting, you are recording. Recording how much it is emitting, what colors it is emitting, what radiations it is emitting, what are the spread of wavelength range. Are they all falling in visible, or some of them are falling in UV region? Had you have a spectacular eye to find the spread of waves in the UV region, that also would give a pattern. And in fact, that has been recorded by a photographic plate, a sensitive photographic plate, which is UV sensitive, which is IR sensitive. So you can develop by a sensitive photographic plate. Though not in a screen, you can record the visible radiations. You can do that in a screen, a black screen you put, you can see the colors. But UV radiation spread, IR radiation spread, इसका भी विबज्योर है, पर लेकिन विबज्योर नहीं है, इसका स्प्रेड है. सो स्प्रेड दिखने के लिए, देखने के लिए आपको फोटोग्राफी प्लेट यूज करना पड़ेगा, which is sensitive to IR, sensitive to UV. Nowadays, that also is not being done. Spectrometer is there to give a graph, curve, which radiations are being absorbed and what is its intensity. This wavelength is absorbed at the maximum intensity, this lowest intensity. So you get a graph having a maximum point and starting from a minimum point to maximum and then falling down, absorption peak, and also the emissions peak. But for beginners like you, I will tell you something different to make you explain better about absorption wave. Just hold on. Now, emission wave is of two types, or both. Both is again of two types. One is called the continuous, which I showed you. This is called a band spectrum. There is no gap in between. The example is solar spectrum. And the spectrum from black body radiation. I will talk about black body radiation later. Any coal, supposing you heat the coal, koala, you heat to red hot, it will produce radiations. Infrared, visible, these two radiations will come out. It will glow with a light, so that means visible. It will be heated up, that means IR. So if you pass through the prism, you will find a continuous pattern. It's a continuous pattern, not a discontinuous pattern. IR you cannot see. You can record it either in a spectrometer or in some special photographic technique. But visible you can see. So that's continuous. Solar spectrum is continuous. Black body radiation is continuous. And any आजकल तो नहीं दिखते हैं हम जब छोटे थे, आजकल आप दिखते हो क्या? That is we funnily call doom. 200 power doom. I mean, it looks like it works on a tungsten filament. There is a filament inside, and when that filament with high resistance, the electricity passes through, it produces light. So those are called incandescent lamps. So those lamps are not available now in the entire world. They are obsolete now. LED has come. So but I'm not talking of these LEDs. I'm talking of the incandescent lamp, the filament lamp. So those also will produce the light. When you analyze through a prism, they will show you not a white band like Vibgyor. Sun is the greatest thing. But that may be a small range, but continuous, no gap. But there is another possibility, is discontinuous. This is called a line spectrum. Now, this example is solar, There is no need to further explain. Now, this I will explain. Supposing you go to a dark room, right? This is a Bunsen burner. This is the blue flame. It's not emitting any. And now what you do, you put some sodium chloride crystal in a tong. Take some sodium chloride. You can't hold it inside flame in your hand. Your fingers will burn out. So you take in a tongue, a crystal, and sew it, put it inside the flame. So you will find a yellow radiation will come out. Golden yellow radiation. And when that golden yellow radiation will be passed through a prism, you put a prism inside a dark room, not allow the sunlight to fall, only analyze this yellow light which is coming from the sodium chloride, put inside a flame. So this golden yellow light, when passed through a prism and then you hold a screen, you will find it will be segregated, it will be dispersed into two lines, only two monochromatic lines. One is 5980 angstrom, 5890, 5890, 5980. The other one is this is a screen that you are holding, 5890 angstrom. The other one, yellow line. All these are yellow. I am drawing in red, but this yellow line. This 5896 angstrom. This is called the D1 line. This is called the D2 line. The D1, D2, the namings have come from spectroscopy, which we will learn later. So D1 and D2 line, these are the two lines which represent sodium. In fact, sodium is the hero. Chloride ion is not emitting any color. Sodium, in the flame, in fact, what happens, let me tell you in advance. In the flame, sodium ion, which has already lost one electron, sodium has lost one electron to chlorine and become sodium ion. Now it will get back that electron from chloride ion and getting both of them converted to neutral atoms, NaCl, not in the ions. In the flame, then don't remain as ions, they become atoms. So that unpaired electron, I'm just telling unpaired, never mind if you don't understand. That unpaired electron now, which has been returned back to sodium, that goes to a higher level. We will study that, what are the higher levels, and it will return back to the lower level. When it returns back to the lower level, it emits characteristic radiation, and that for sodium it is yellow, and it contains only two transitions representing two radiations, and that is yellow region, and some potassium will give similar three to four lines in the violet lilac region. Every element, when or in its compound, even if you take a compound, pure crystal, put it in the flame, it will be atoms. Its lost electron will be replenished back, and they will be getting back their electrons, become neutral, and the same electron will be excited to the higher level, and when they return back to the ground state, they will emit characteristic radiations. Their energy difference are different. We'll be studying that. Therefore, their lambdas are different. When lambdas are different, their colors are different. Therefore, the spectrum of each individual element or compound is called the fingerprint. Just like two twins, Jara, bhai ki bhoni, two twins, they will be distinguished by that thumb impression. Fingerprint, they are different. Fingerprint is unique to every individual. In the same manner, the spectrum is unique to each element or compound, which will definitely not match with any other. Maybe in the same red region, same violet region, same blue region, but they will not match. The blue contains infinite number of radiations. They will not match. I will show you. So you have emission spectrum, you have absorption. I'm not talking much about absorption now. Emission spectrum is also called hot spectrum. To distinguish between the two, I use the word hot. It means when you heat it, excite it, they radiate, then that is called emission. This is called cold spectrum. There is no need to heat it. You feed all, it will consume. Then what it will consume, you can know. And nowadays, spectrometer records what it will consume. In earlier times, it was determined indirectly. You have given all the vegetables from Chhatra Bazar. From the market, you brought all vegetables, fed a particular person. But he or she cannot take brinjal and lady's finger. These two vegetables she doesn't like. So he emits. So from the radiations which is not observed, which is emitted, transmitted, I'm sorry, which is transmitted, not emitted, transmitted. From the transmitted radiations, we know what are absorbed. That means, supposing you do one thing, sodium chloride, let us take a cold spectrum. You take sodium chloride solution in the dark room and a small hole in your home to allow a thin ray of sunlight to pass through the sodium chloride in a dark room. The sodium will absorb all not absorb infinite number of radiations. It will absorb only two characteristic radiations. That was given when it was falling from the higher state to lower state. Now it will go to the higher state. So it will take same D1 line, D2 line to be excited and leave the rest. It will absorb D1 line and D2 line. Absorb. Eat away. The petrich, पेट में है. And this, when you pass through a prism and record, same behavior will be found, but only two lines will be missing. They will be appearing dark lines will be coming. So from the look of that spectrum, all behavior is there, but there are two lines, dark, no color. So looking to the two dark lines, you will identify, oh, it must be sodium because 5,890 angstrom is missing, 5,896 angstrom is missing. Oh, that means the culprit is sodium. So from the missing lines, that was the norm. That was being done long ago. Nowadays, nobody bothers. If you want absorption spectrum, cold spectrum, put it in the spectrum. It will show the peak. From the peak, you can tally सोडियम का एब्जॉर्प्शन पीक क्या है, तो मैच करने से पता चल जाएगा ये सोडियम है. Or if you want a hot spectrum, you take the emission and take the spectrum. I mean, you pass through a prism or a diffraction grating, then you analyze what colors are coming. If it is visible, you can put it a screen and see. If it's not, then you can allow the spectrometer to record and give you a graph. Earlier, photographic methods were used to develop any such lines coming from the UV region or IR region or any other region. Now, so with this much of a thing, I think I should put an end to. We have done this lecture, which you will be doing some questions. I have put it. Planck's quantum theory. We have already done some questions, answers I have already done. One thing I forgot to tell you is, because while you are a certain source is emitting radiation, or it is propagating, or somebody is absorbing, hundreds and thousands of photons are falling in every second. So for one photon, the energy is h nu, hc by lambda, hc nu bar. It is for one photon. But for multiple photons, then in questions you will be asked, this much of energy was absorbed by a certain element. How many photons it absorbs? Because it absorbs in only photons. 1, 2, 3, 4, 5, 6. Discontinuously, you count how many photons it is absorbing or emitting. Absorbing, it going to higher level. When it is falling back, the electron is falling back, it will be vomiting out, but in single packets, not continuously, one after one after one after one. So for n number of photons is equal to nh nu nhc by lambda nhc nu bar, where n is the number of photons. So in some calculations, you'll be asked to find out the number of photons those have been absorbed or emitted. You will find such questions. So n for one photon, this is the relationship. For n number of photons, you multiply by n. So this we have finished. I will give you these things. Some assignments is there for practice, and answers are also there in between. We can make practice. So it's not a very binding from my part that you all do all. But if you want to follow me, then it is better that you do some, at least to have a practice. Even if you can't do all or even one, you can join. There is no harm, because and this second one also we have done. Atomic spectroscopy, that we have done. I have shown you beautiful pictures. Emission spectrum. This is the Vibgyor, and continuous and discontinuous, D1 and D2 line of sodium. In the coming program, you'll see hydrogen spectrum. That is also discontinuous. Spectrum of each individual element is also different, and they will not match with any other. They are the distinguishing mark of a particular element. And solar spectrum, blackbody radiation spectrum from an incandescent ball, like the doom kotha kohti filament ball. Ethi hydrogen gas niyaଯାଇଛି. This hydrogen gas is subjected to high energy. It is emitting some reddish radiation. देखियो reddish, white देखा, but when you analyze that through prism, it will give you some distinct lines, not continuous like solar spectrum. One line at orange region, the other line at the blue region, then indigo region, then a few lines. Maybe 4 or 5 lines you can distinguish, others you will not. We will study more about all these in our next program, hydrogen spectrum. So the first line here in the red region, and then orange region actually, then in the blue region, then finally in the violet region. This is the hydrogen spectrum. The hydrogen is producing light. It looks like continuous. I mean, it looks like containing an infinite number of radiations. No. When you analyze through a prism, दूध के दूध पानी के पानी पता चल जाएगा. It's not like solar radiation. It's not like continuous spectrum. It is an emission spectrum, no doubt, like solar spectrum, but a discontinuous spectrum containing, like sodium spectrum. Sodium was having only 2 lines, D1 and D2. But here it will be containing a few more lines, but widely different. First line, second line, the gap is more maximum, then the gap reduces, then slowly it converges. After 3 to 4 lines, you'll find the lines will be converging with one another to form a thin band. We'll be doing that later. So I'll be showing here that hot spectrum, which is called the emission spectrum, and that is the fingerprint of any element or compound that gives the true identity of that particular. This is the yellow line, D1 and D2 line, 5890 called D1 line, and the second line is 5896. Similarly, strontium has these 4 lines, 1, 2, 3, 4, 5, 6. Nobody will match with nobody. Manganese has different lines. This is copper lines, beryllium lines, titanium lines, and it's asking you an unknown element spectrum is given, the hot spectrum is given. Which one you match? Undoubtedly, it exactly matches with strontium. So the unknown spectrum is definitely the strontium spectrum. So the cold spectrum is just is not very popular for you now, but for us, I mean, for higher level, it is very popular. And now take the sunlight. This is the continuous spectrum. This is the hot spectrum of, say, some hydrogen gas. This is hydrogen gas. It is excited, heated, so it is emitting some radiation, and you are analyzing through a prism. Everything appears dark excepting few lines. Now, same thing you are doing in cold. You are allowing the entire sunlight. This is sunlight to pass through. It will absorb its characteristic. These lines will be eaten away, leaving behind the entire Baghanisa Honala. All the behavior will come, this pattern, excepting these missing lines, dark lines. So from the dark lines, आपको indirectly पता चल जाएगा ये कौन है जो ये dark lines produce किए हैं. तो वही है हाइड्रोजन. अगर हाइड्रोजन है तो ये तो हाइड्रोजन मुझे नहीं लगता ये हाइड्रोजन है. हाइड्रोजन का जो है पहला लाइन शुरू होता है ऑरेंज से, ये तो शुरू हुआ है ब्लू से. जस्ट फॉर कॉन्सेप्ट पर्पस. Now see your continuous spectrum, Baganisa, Honala, Bhipchio. This is the emission, discontinuous. Discontinuous but emission. The colors are visible. But here no, all colors excepting the dark lines, the missing lines. So these two will give the same information. But while vomiting mode, this is eating mode. And the rest of the band, solar band, you have to take the help of solar spectrum. You have to take the help of some continuous spectrum to find the absorption spectrum of a particular element, so that you find the missing lines in the spectrum produced after the absorption. So these are the same thing. Then in the next class, we'll be talking about hydrogen spectrum. So as I plan that our classes will be from 4:30 to max 6, but our break will be from 5:30. 1 hour के बाद हम break करेंगे. Then any questions you are wanting to ask, you can ask. Then next time we will be discussing hydrogen spectra and Bohr's theory. Now you will find, just I'm giving you a short picture. This is the Balmer series. The first person to find hydrogen spectrum is discontinuous is Balmer. You can call it Balmer or Balmer. I don't know how it is pronounced. Let me ask Google. Google is a terrible guy. Baltimore. So I ask you Balmer. So, yes, Balmer series. Balmer. Yeah. L is remaining side. Balmer. US pronunciation is Balmer. And UK pronounces Bamu. Okay, we say Balmer series. Balmer series is the first line in the orange region, the second line blue, and then convergence occurs. Now what happens? Let me tell you in advance. What happens really? Just in 2 minutes. When we have hydrogen gas, we have hydrogen atoms, thousands and thousands of hydrogen atoms, not one. And when we apply energy through electrical means, all types of photons are available. So in some atom, the electron is in the ground state. The first cell is called the K cell. So it is excited to the second level. This is called the first excited state. In some other atom, it goes from first to second. I mean the third cell, that is the second excited state. In some other, from first to fourth, the third excited state. First to fourth, fifth, first to sixth, first to seventh, first to ninth, first to all transitions occur, because there are thousands and thousands of atoms. And the photons available in our electrical method is infinitely large. All varieties of rasgullas, 5 rupee rasgulla, 10 rupee rasgulla, 15 rupee rasgulla are all available there. So different atoms are excited to different higher levels, but they cannot remain. They have got a lifetime. They will return back. So during return journey, we are taking the emission. The color that we are seeing is the return journey. In some cases, the atoms in which the solitary, only one electron is there in hydrogen, which was there in fourth cell, is coming directly to one. In some other third cell, directly to one. In some other fifth cell, directly to one. So any journey directly from higher to one, that will lead you a particular series. It's called the Lyman series. That won't be visible. That has to be recorded in a photographic plate. And the Lyman is another scientist, much after Balmer. He found similar, exactly similar series. Like the pattern is similar. The first and second gap is more, second to third gap is reduced, third to fourth is still reduced, and then after a few lines, then merging of lines occurs. You can't see further growth of lines. That means it is a continuous, discontinuous spectrum or a line spectrum. But pattern is this convergence. Similar lines he found in a different region, UV. UV region he found, it's called the Lyman series. Those are the transitions from all different higher energy levels to the first cell. We shall be calculating using the Bohr theory, the mathematics of Bohr theory, and we'll be calculating that. And similarly, Balmer was the first person to record in visible spectrum that all transitions from different higher cells directly to the second cell, 4 to 2, 3 to 2, 5 to 2, 7 to 2, 9 to 2, 10 to 2, all culminating, ending at 2 will have all energy difference we will calculate will be falling in the visible region, and the pattern is. And then after some years, Paschen, he found in higher region, similar pattern, but in higher region. That means culminating in 3, 4 to 3, 5 to 3, 6 to 3, 7 to 3. This is called Paschen series in the infrared region. After some years, Brackett, another scientist came, because IR is a big region, from 7,600 to 6 times 10 to the power 6. It's a huge region. So Paschen found in the first part of the IR region. The second part, Brackett found another series, similar type of pattern that he proved that it is culminating in 4, 5 to 4, 6 to 4, 7 to 4, 8 to 4. All transitions culminating in the fourth cell will produce similar patterns of lines in another part of the IR, much away from the Paschen series. That is called the Brackett series. Then after some few years, P fund, P-F-U-N-D, I think P will remain silent. Fund. He came and found another pattern in the last part of IR. Not last, in another part of IR, higher part of IR. That is called the P fund series, all culminating in the fifth cell, 6 to 5, 7 to 5, 8 to 5. So same pattern. And then after a few years, maybe in the early part of 20th century, Humphrey, he found another similar series, all culminating in the sixth cell, 7 to 6, 8 to 6. So these gave rise to a number of series. Balmer was the first person to record in visible region. And he gave a empirical formula. We'll be doing that. So this is the entire spectrum. This, Lyman, and this is Paschen bracket. And I told you that why sodium chloride emit the same D1, D2 line as sodium metal, because in the vapor, the electron transfer occurs, they remain in the atomic state, and that unpaired electron of sodium that is excited and it returns back, it produces two characteristic transitions, D1 and D2. Chlorine doesn't show any radiation in the visible region. That doesn't mean that chlorine is not excited. Chlorine shows all transitions in the UV region, in the other regions which is not visible. So it doesn't produce any visible spectrum. So that is our today's program. Tomorrow, next time on Friday and Saturday, that is on 9th, we'll be completing the very, very interesting Bohr's theory and the mathematics and their calculations. Bye-bye. And guys who are watching from the TV, and you guys who have joined me at 4:30, I congratulate you. It's not that easy to. I'm doing at 4:30 for two reasons. One, you'll be able to join in your school and coachings. Two, to see that you are really serious to join me in live. Do you have any question to ask? Yes or no? Not for today? You understood everything?
Yes, sir.
How did you like? Is okay?
Yes, sir. Very
So,
nice, sir.
okay. So to motivate me, you can put a little comment off and on. So that is a mutual motivation. So see you next time. Bye bye. And ask all your very bright students, serious minded students to take the benefit of this program, which I enjoy in the early morning program. Bye.
Thank you, sir.
Sir, Pranam.
Pranam.